Okay, so this is the second video from chapter 16. This time we're going to look at just a couple electric field problems. So we were looking at the effects of forces only in the last problem. Now we're going to be looking at force fields. Not too different though, so you should see the similarities. So in this first problem, we want to consider the effect of an electric field kind of at this spot, point P, due to these two charges. We got one negative charge 2 centimeters away and a positive charge that's about twice as big, 8 centimeters away. So the idea is what's the direction and magnitude of the E field right here, or anywhere else for that matter. I mean, the one thing about this problem that's nice is the geometry is easy since they're all in one straight line. Okay, so since we're talking about electric field, from the reading guide you should know that the electric field is K, that same K constant, and then you just have to think about one charge at a time, and then you divide by R squared. So it's almost like Coulomb's law, but not quite. So for this one we have 2-point charges, so I think we're just going to add those up. So the total field is going to be just 2-point charges added up. And I think it's both. Let's think about which direction it's going to be flowing. So remember, it's like you always think like the field is like positive flow. That's the convention we're going to use at least. So like positive flow for the field. So right here, isn't that negative going to be sucking the field this way? And then at that same spot, that positive is also going to be pushing the field this way. So that's why we're going to pretty much just add them up. It's going the same way. The field is flowing that way for positive charges. Okay, so let's just factor out a K, I think, and let's see what we've got. So we've got charge 1, let's say 25 coulombs. Oh, microcoulombs again. 25 times 10 to the negative 6th, and that is what, 2 centimeters away, so 0.02 squared on the bottom. Is that right? I think so. Let's make this bigger. And then we're going to add, since the field's going in the same direction, that 50 microcoulombs. And that's located 8 centimeters away, so 0.08 squared. And we'll have K, 9 times 10 to the ninth, outside of that, so that should give us the field strength right there. So let's see, I think we get about 6.3 times 10 to the 8th. And remember, this is not a force, this is the electric field. So remember, if you're thinking about how forces relate to the field, just go back to the main definition of an E field, and you can do it in vector form or not, but the magnitude, if you're not doing it in vector form to include the direction, is just the force on a charge divided by the magnitude of that charge. So that's what the electric field is. So if you want to translate this back into forces, you can just multiply the charge up there, the overall charge. So we're going to do that on some problems too. But anyway, that gives us units are newtons divided by coulombs, if you think about it like that. Yeah? So there's our first part. The second part says, what if an electron is at point P? What's its initial acceleration? So first, I think we should consider which direction the electron would go. Since the field is flowing positively this way, that's the way positive particles, like a proton, for instance, or anything else that's charged positively would flow. So an electron's going to flow to the right, isn't it? So let's say to the right. So we can remember that. So even though our field's flowing to the left, since that's for positive particles, an electron that's released is going to go that way. And we are supposed to figure out the magnitude of its acceleration. We already know the direction is going to go straight that way. So if we want acceleration, acceleration from Newton's second law is force divided by mass, right? F equals ma. The only question is, how do we get the force due to an electric field? Well, isn't that right up here? Don't we just do what I said a second ago and multiply? So we get the field magnitude times the charge divided by the mass. So the field magnitude we just calculated. The charge is well, what's the charge on an electron? So I think maybe that's in the front of our book. That's maybe the first time we've seen that this year. Charge on an electron is E. Oh, and no, we saw it before. So anyway, we're going to go 6.3 times 10 to the 8th. That's the field strength. You know, maybe I will do this in... should we keep our units on this one? I think we should. Let's keep our units on. Let's put them in green. So that's newtons per coulomb, right? Okay. A little bit of dimensional analysis. Charge is going to just be in coulombs, right? So charge on an electron, whether you look it up in the front or whatever, it's the symbol E, and E is measured at 1.60 times 10, pretty small, to the negative 19th. It's charged, so it's coulombs. And then we've got mass is 9.11 times 10 to the negative 31st. You can also look that up in the front of the book or wherever else. Kilograms. Obviously an electron is a really small mass. So you can see that at least these went away, and newtons per kilogram, isn't that an acceleration? If we remember, what are the units for force? Isn't force isn't newtons kilogram per meter per second squared? So like newtons would, like the kilograms would cancel out and stuff. But anyway, I'm not going to do too much dimensional analysis. So get your answer. And it's 1.1 times 10 to the 20th meters per second squared. So we can see that this electric field would accelerate that electron a lot to the right, right? The field's going this way, the electron's going to fly out that way. Okay, there's one example. Let's look at one that's a little more complex. I think this is really similar to that last one we looked at when we weren't doing fields, we were just doing forces with Coulomb's law. So I drew this a little poorly, sorry about that. So we've got one axis up here, one axis down here in 2 dimensions. 2 charges only. These are just different points in space you might want to consider. So we're going to have a positive charge and a negative charge, same magnitude on this axis. And I've got some measurements in there. Okay, so part A is what is the total E field due to both of those up here at point A. Okay, so the E field, remember we're thinking positive flow, so that means the bottom charge down here is going to push it out this way at that spot, and this negative charge here is going to try to suck you in that way at that spot, so that's the way positive charge is going to be flowing. So once again, we just use the formula for the field strength, and we plug in, so what's that going to be? 9 times 10 to the 9th, I'm just going to say K, okay? So 9 times 10 to the 9th times Q1, what is that? Negative 50, let's go magnitude, 50 times 10 to the negative 6th. And then that radius we said is 60 centimeters. This is just like almost identical to the other problem. We're just doing fields now. So that comes out as 1.25 times 10 to the 6th. It's a field, so it's newtons per coulomb. Same thing here, K. Oh, and this is going to be the same thing as up there, just the radius is different. We're just getting the magnitude right now. The directions are obviously, we're going to have to think about them. R squared, that one is 0.3. So you might guess that that's going to be a stronger field because the radius isn't as much. And it is. It's about what? 3 times bigger? 4 times bigger? Yeah. Okay. All right, so there's the magnitude. What's the total E field? So how do those interact with each other? I think we've got to do vectors just like we did in that previous problem. Excuse me, in the first video that we had. So let's think about like the x and y direction. So let's just say EX. Let's try to do this fast. The overall x direction. There's none from this guy, so none of that is x direction. That's all y direction. We've only got the x component to that. Let's put our triangle in there, make it big, kind of exaggerate. So let's see. Do we know this angle? I think that we're just going to say we're given that this angle is 30 degrees. They've got to give us some kind of angles in this scenario to make this work. Okay? So anyway, let's say they gave us that was 30 degrees. Then the x component would be the cosine, right? So the cosine of that 30 times this guy, that was charge 1. So times 1.25 times 10 to the 6th power. Okay, so I got 1.1 times 10 to the 6th is left. All right, then the y direction, they both contribute to that, right? We've got like this guy trying to push up, so we'll say that that's the positive direction, so 5 times 10 to the 6th. And then this guy's trying to pull down in terms of the sine of 30 degrees. This much. So you get 4.4. Okay, so then the overall field, you'd use the Pythagorean theorem and say E at A total is going to be the square root of EX squared plus EY squared, and plug that in your calculator. I'm not going to actually show it there, but you plug it in and you get about 4.5 times 10 to the 6th newtons per coulomb. Okay, what about if we consider the E field at point C up here? So let's think about that again. So this guy, again, if we're thinking in terms of a positive charge, this guy's going to try to suck it in like that. That guy's going to try to push it out. It's going to be kind of like this, isn't it? Trying to pull it in, and this guy's going to be trying to push it out. So let's just consider the geometry here. So they told us that this is 40 centimeters. Let's figure out how long this is just before we move on too much. So this, pretend that's a triangle. Haha. So if this is 26 and that's 30, the Pythagorean theorem says that that line is going to be, let's see, square root of 26 squared plus 30 squared. Use my calculator. Oh wow, I got like 39.7. That's so close to 40 that I think we're just going to ignore the y components. Do you know what I mean? Ignore the y components. So in green here, I'm going to componentize this. This guy from the positive charge is kind of pushing out like that, right? So in other words, like its y component's going this much up. This guy's pulling down, so its y component's going down. Since those triangles are pretty much congruent triangles, so close to 40 there, and the charges are just opposite each other. They're the same magnitude. I think these y's, these greens that I have on there, are going to cancel out, okay? So in other words, they're going to cancel out completely. So I think we only need to worry about the x components on this one. So we get these guys back in there. So we've got them both pushing out. Isn't it going to be the same x component since their magnitudes are the same also? So we've got like two of those. So let's just calculate one x component, and I think that should give it to us. So down here, if we go, I guess I'll do it in green. If we do an x component, it's going to be, well, let's just get the overall magnitude first. So for either one of them, the overall magnitude is going to be k, it's 9 times 10 to the 9th, times q, don't we even already have it? Only thing that's different is the radius, so we're going 0.4 for either one, right? So if you do that, you get 2.8 times 10 to the 6th. Okay? So there's the overall magnitude of either one. We just want their x components and then double that. So let's just take the x component from either one, that's going to be what? So should we think about what this angle is? So what if they didn't give us this angle? We do have the triangle dimensions, so I think we could figure it out. So we really want like this angle right here, right? But isn't that angle, if we continue this down, the same thing as this angle over here? So we can just think of this triangle and get it. So in other words, the tangent of that theta that I've defined is going to be what? Opposite is 4. So this is like a little clip I added because I made a mistake. So as I was saying, we're trying to find the x component here, right, that we have in green. So I defined this angle theta, and we brought it back down here, and I don't know why I looked at the triangle incorrectly, but the opposite is this distance, which is 30, not 40, as I had the first time, and divided by 26. And if you take the arctangent of that, you get about 49 degrees. Okay, so now if we finish, we're going to say that that is cosine of 49 degrees. That specifies our direction outwards, and times the magnitude, which we just did, times 2, because we had the effect of both of these charges producing that same vector outwards. This negative one is sucking the field that way. Does that make sense, right? It's sucking positive particles that way, and this positive charge is pushing positive particles that way, but the net effect is basically the same. So we'll just double it. Let's see what we get. So cosine of 49 times 2 times 2.8 times 10 to the 6th power. So I got, I'll just write it out this time, 367,393.562. So that's millions, so times 10 to the 6th. So significant figures is 3.6, 3.7. I'll go 3.7 times 10 to the 6th. Newtons per Coulomb. Remember what we did is we calculated the magnitude of the electric field strength at point C. We could also go do point B if we were curious. But what do you think? Point B. So at point A, the magnitude of the electric field was positive particles would be going with kind of this much field out. Well, if we add those vectors, it'd be kind of going like this, right? We could find the direction if we wanted to by going using the components. And in this one, it's going to be going kind of like straight along this axis, I think, since that's so balanced. And that's where particles are going to be pushed. So, and in the second one, you can see that it's a little bit weaker. So if we thought about point B, I think positive particles, let's see, this guy'd kind of trying to suck them in. That guy would be trying to push them out. I'm thinking it'd probably be more like this at point B if we did that one. But anyway, one more video might be useful to you. See you next time.